Hello and welcome to this video for Chemistry 20 in the Solutions unit. In this lesson, we are going to look at writing net ionic equations. Now, in order to write a net ionic equation, there's actually a series of steps you have to go through. The first step is to write what we call a non-ionic equation. This is the kind of equations you learn to write in Science 10. So let's say you're told lead 2 nitrate, because lead is multivalent, so it would say lead 2 nitrate is reacting with potassium iodide. This is a double replacement reaction. I'm actually going to quickly write this out. So let's say you're told lead 2 nitrate is mixing with potassium iodide. Just a little review for writing reactions. These are both ionic compounds, so I have to again look up their ion charges and balance their ion charges. Lead is multivalent, so it's telling us in Roman numerals which charge to use. Nitrate is NO3 minus 1. So the formula for lead nitrate, to balance the ion charges, I would need 2 nitrates to make that happen. Now, this is a double replacement reaction because it involves 2 ionic compounds mixing. So what that means is you have to check your solubility chart. When you have nitrate, nitrate is aqueous with everything, so that makes it a little easier. This was iodide. I didn't finish my sentence. Potassium iodide. So that's potassium K plus and I negative. Those charges balance, so I only need 1 potassium with 1 iodide, and that is my second reactant. Now, in a double replacement reaction, the metals switch. So my potassium will go with the nitrate, which will be soluble. Again, I'm balancing my charges. Potassium is 1 plus, nitrate is negative 1. And my lead is going to go with my iodide. Lead again has the 2 plus and iodide has a negative 1. So to make those balance, I need 2 iodides. Now, when you check your solubility chart, this compound is insoluble, so it is solid. Then we finish by balancing our equation. I have 2 nitrates on my reactant side, so I need 2 nitrates on my product side. That gives me 2 potassiums, so I can put a 2 in front of my potassium iodide, which also gives me 2 iodides, and there are 2 iodides on the product side, so it balances. So writing an equation like this, I'm going to erase this and put it up a little neater. Writing an equation like this is called a non-ionic equation. Okay? Notice how the products, from what I wrote versus here, they switch the 2 products. That's fine. It doesn't matter the order you write the products on. Same with the reactants. I could switch the first 2 reactants. Okay? So that is step 1 to writing a net ionic equation. You are writing the non-ionic equation. Now, non-ionic equations aren't fully accurate because they are showing these compounds as if they're staying whole compounds. And we know soluble ionic compounds actually dissociate in solution. So what does that mean? It means they split apart into free ions. So if I start with my non-ionic equation again, I can convert it into a total ionic equation by going through and splitting it up into the ions that make up that equation. So this again was our non-ionic equation. I follow through to split it up and make a total ionic equation. So what that means is any soluble ionic compounds are going to break apart or dissociate into free ions. So remember, as free ions, we show them with their ion charge, and they are aqueous. So I have a Pb2 plus aqueous ion. I have nitrate ions also, so I'm essentially going through all of my aqueous compounds and dissociating them, okay? I have 2 nitrate ions. That's what the subscript of 2 there meant. So that becomes a balancing 2 in front of my nitrate. I have a balancing 2 in front of my potassium iodide, so it goes with both of those ions. I have 2 free potassium ions because this compound again was aqueous. Aqueous compounds always dissociate into ions if they are ionic. Now next, I have PbI2. That is an insoluble product. Insoluble products do not dissociate. they stay whole solid products, okay? But my next compound is soluble ionic, so it will turn into free ions. 2 free potassium ions and 2 free nitrate ions. Okay, so that is the total ionic equation. It shows more accurately what these substances are really looking like in solution, because in solution, if it's a soluble ionic compound, it's not staying a whole compound. It's splitting into ions. The next step is to write what we call the net ionic equation. The net ionic equation purpose is to show only the change that's taking place, okay? So any spectator ions, ions that are not changing in the reaction, are canceled. So this was our total ionic reaction from the previous slide. Looking for spectator ions, I'm looking for ions that start as a free ion and end up as a free ion. My nitrate on the reactant side is a free ion, and on the product side is a free ion. So they are spectator ions and cancel. Same with the potassiums. There's 2 potassium ions on the reactant side and 2 free potassium ions on the product side. So they also cancel. So the spectator ions in this reaction are the potassium ions and the nitrate ions. Okay, if you're asked to identify the spectator ions, they are the ones canceling. What we are left with becomes our net ionic equation. So what we are left with is Pb2 plus and 2 iodide ions on the reactant side, because the other reactants have canceled. And on the product side, all we have is Pbi2 solid. So what this is showing is that my solution started with free Pb and iodide ions, but when they met to each other like magnets, they stuck together and made a solid, what we call a precipitate. Okay? A precipitate is a cloudy, insoluble product that turns a solution cloudy because the solid particles are floating around in the solution. So when I mix these two solutions together, it's all of a sudden going to turn cloudy, and that's what's making it turn cloudy, that precipitate, that insoluble product. Let's do a couple of examples starting from the beginning. So let's say I'm told sodium hydroxide and aluminum nitrate are mixing. So I'm going to start again with my non-ionic equation. Again, these are ionic compounds because I have a metal. So I need to balance ion charges. Most compounds you're going to see in Chem 20 are ionic. So sodium hydroxide is NaOH. This is another double replacement reaction because it's 2 ionic compounds. So I check my solubility chart. When you look up hydroxide, it says group 1 ions, which sodium is, are aqueous. Aluminum nitrate would need 3 nitrates to balance the 3 plus on the aluminum, sorry. Nitrate compounds are also always aqueous. What's going to happen, my metals again are going to switch. So my sodium is going to bond to my nitrate, and their ion charge is already balanced because they're 1 plus and 1 negative. My aluminum is going to bond to my hydroxide, but my aluminum has a 3 plus, so I need 3 hydroxides. Remember, when you need multiples of a polyatomic ion, you put it in brackets. And that compound is insoluble. Okay? Balancing this reaction, I need 3 hydroxides and 3 nitrates, and that's balanced. Now we can write our total ionic. So I have a 3 in front of this soluble ionic compound, so it's going to dissociate into 3 free sodium 1 plus aqueous and 3 OH, negative 1 aqueous. My next compound is also a soluble ionic compound, so it will also dissociate into Al3 plus aqueous and 3 NO3 minus aqueous, right? That 3 there becomes the balancing coefficient for nitrate. On my product side, I have another soluble ionic compound. That 3 again goes with the sodium and the nitrates. You should always have the same number of each ion on each side if you balance the reaction properly. My last compound, though, is insoluble, so it is not dissociating. It is staying AlOH3 solid. Okay? Now, I'm going to cancel my spectator ions. My sodiums cancel, my nitrates cancel, and so our net ionic, or what we're left with, is 3 hydroxide ions and aluminum 3+ ions. Those are my only reactants. My product is AlOH3 solid. Okay? So that is very similar to the first example that we did, where I am doing a double replacement reaction, and we are producing a precipitate. Okay? So the first ions that were soluble are joining together to make that solid product. Now, the other type of reaction that you can see commonly in these questions is a single replacement reaction. Okay? So we are starting with fluorine gas. Remember, fluorine is one of your diatomic elements. And by the way, this is an element that I'm starting with. Elements are always neutral atoms, which means that they are not ions. So they do not have an ion charge. Okay? So starting with my non-ionic equation, fluorine is F2 and it's a gas. And now I have ions because I have an ionic compound of sodium chloride. So my Na and Cl will bond together, balancing one of each. In a single replacement reaction, whatever your element is, nonmetal, will switch with, therefore, the nonmetal in the compound. So my fluorine and my chlorine will switch. My chlorine will become elemental chlorine, which is Cl2 gas, and my sodium will bond with my fluoride. I'm forming fluoride ions now that I'm making an ionic compound, which have a -1 charge, so they balance with my sodium with just 1. Now, to balance this equation, I need to put 2's in front of my compounds, and then it's balanced. So when I get to my total ionic now, again, my element form is not ions, okay? When you have an element, it is an atom. It stays exactly the same. The only time you dissociate and form ions is when you have a soluble ionic compound, okay? So I'm breaking my sodium chloride into 2 sodium and 2 chloride ions, but my chlorine gas, again, is staying a whole Cl2 gas. Again, I have 2 sodium ions now and 2 fluoride ions because it was a soluble ionic compound. So again, the only time you have ions is if you have a soluble ionic compound. When you have an element, okay, it stays an element. It's an atom. It does not have a net charge. Don't put a net charge on it, okay? Don't dissociate it. My only spectator ion now is sodium. So what I have left is fluorine gas reacting with 2 free chloride ions, and what is being produced are chlorine atoms making chlorine gas, and the fluorine that started as atoms is becoming ions. Remember, ions have a net charge, atoms don't. What's actually happening here is a transfer of electrons. When you have a negative charge, you have extra electrons, okay? That's a whole unit in Chemistry 30. So it's important to know, again, when you have an ion and when you have an atom. When they have no charge, they are an atom. When they have a charge, they are an ion. Okay? And that is it for writing net ionic equations. I hope that was helpful. Thank you for watching.